Hello everyone, my name is Jesús Rueda-Becerril. I'm a postdoctoral fellow at Purdue University at the Department of Physics and Astronomy. Today I'm going to talk about the numerical approach that I have developed in order to study radiative cooling in relativistic outflows. The outline of my talk is first talk about the introduction, talking about the astrophysical object that I would like to discuss today. Then I will talk about the numerical method that I have developed. Then I will talk about the astrophysical application of this numerical tool, and I will finish with some conclusions. The astrophysical object that I would like to study today are gamma ray bursts. These objects are the most energetic that have been observed up to date. These objects are super energetic explosions that show different phases. In the first few seconds they show most of the energy, and afterwards they show a decay in the light curves. It is thought that in this later stage, the afterglow, accelerated electrons interact with photons in the surrounding medium or photons in the same outflow, producing ultra high energy photons through inverse Compton scattering, transferring part of its energy to those photons. The inverse Compton scattering cools down these electrons, affecting the distribution of them. However, if these electrons are extremely energetic, then no longer we can apply the classical Thomson regime. We need to apply the Klein-Ishina corrections to the radiative cooling. However, these corrections are highly nonlinear, and therefore numerical tools come handy in order to consider these effects in an evolutionary system. As a way of testing and comparing, on the right hand side, the numeric approach with some analytical approximations for two different radiation fields, black body and monochromatic. In the blue line we can see the Thomson regime, in the green line we can see the analytic, and in the orange we can see the numerical approach. So we can see that the orange line transitions from the Thomson to the Klein-Ishina and even to the deep Klein-Ishina regimes. And as an application, I have taken the best fit for the gamma ray burst observed by MAGIC last year in January, and I have taken the fireball model for gamma ray bursts and evolved a distribution of particles with my code and taking into account the Klein-Ishina corrections. So in these plots we can see in solid lines the simulations considering only Thomson cooling, and in the dashed lines we can see the effects, the results of the simulations with the Klein-Ishina corrections. As we can see for the electrons energy distributions, at the first stages of the explosion, Klein-Ishina corrections has a lot of effect in piling up high energy electrons. These automatically can be translated into light curves. As we can see in the first 100 seconds of the light curves, we can see disparity between the light curves of the high energy bands. And also in the spectral energy distributions, we can see some disparities in many different bands. So as a conclusion, numerical approach matches both the deep Klein-Ishina and Thomson regimes with a smooth transition between both. This numerical code with the Klein-Ishina corrections has been tested in an evolutionary scenario, such as the fireball of the model of gamma ray burst. The Kleine cooling plays an important role during the first stages of the blast wave, as we have seen, and during most of the afterglow stage of the gamma ray burst, radiative cooling is purely Thomson. Thank you.